Welcome to the Deep Dive. Today, we're digging into the 19th century, but not just for history. We're looking at the blueprints for stability and efficiency drawn up by William Thomson. You probably know him as Lord Kelvin.
Yeah, Kelvin was, well, the ultimate applied thinker, wasn't he?
Yeah.
He didn't just give us the Kelvin scale for temperature. He built this fundamental way of thinking about coherence and loss. Stuff we use everywhere now, physics, engineering, you name it.
Right. And our mission today is really twofold. First, how he gave motion this absolute ruler, absolute zero. And second, how he took so many of nature's big questions and, well, framed them as problems you could actually measure, as engineering challenges almost.
Exactly.
Yeah.
And what's fascinating is how relentlessly he pursued this idea of stability. Even when, his models were a bit out there, like his big bet on matter being stable loops of motion.
Yeah, the vortex atoms.
The vortex atoms, yeah. Swirling vortices in this fluid ether. Now, the ether itself, completely wrong.
Famously wrong.
Famously wrong. But the core idea, that identity isn't about solid bits, but about moving patterns that hold together. That was spot on. Really profound.
Identity as a motion knot.
Yeah.
I like that. Okay, so our sources break Kelvin's whole approach down into like 4 pillars. His operating system for the universe, maybe?
You could say that. Pillar 1, putting 0 on heat, absolute temperature. A universal measuring stick for how much things are jiggling around at the microscopic level.
Okay, foundational.
Foundational. Pillar 2, locking down the laws for energy. The first law, conservation, just counting it. And the second law, dissipation, which way things naturally go.
The rules of the game.
Right. Then pillar 3 was his method, metrology, measurement. His famous line, if you can't measure it, you can't improve it. That was his mantra.
Makes sense.
And the fourth pillar, the really ambitious one, was trying to tie it all together with that model of matter itself as these conserved knots of motion, the vortex atoms.
Okay, let's start with that 0 point. Absolute zero. Kelvin connects temperature to this theoretical point where, in the classical view at least, all thermal motion just stops.
Yeah, and that gives physics this universal fixed baseline for the first time.
Why is that baseline so critical?
Because it lets you quantify the agitation rate. If you want to understand any kind of organized behavior, chemical reaction, electric current, whatever, you need to know how much random noise you're fighting against. Absolute zero is like the theoretical floor, the minimum possible environmental leakiness.
Okay, so temperature sets the minimum leak budget.
Yeah.
How does that jump from physics to, like, engineering design? It feels immediate.
Oh, it is immediate.
Yeah.
Because you need a language for performance, right?
Yeah.
And this is where we get these core concepts straight out of Kelvin's way of thinking. You're always balancing S, which is synchronization or coherence, the pattern you want.
The useful structure.
Exactly. Against R, which is resistance or leak the noise, the dissipation, the stuff, trying to break that pattern down.
Yeah.
And sometimes C comes in coupling or capacitance, how well the system holds or transmits the pattern.
So 0 Kelvin is like the lowest possible R, theoretically. When we cool things way down, we're shrinking R, reducing the noise.
Precisely. You lower the temperature, you shrink R dramatically, and what happens then? The coherence lifetime shoots up. That's the quality factor, the Q factor engineers talk about. Q just measures how long your desired pattern S lasts before the leak messes it up. That's why you see these incredible effects, like superconductivity, only at cryogenic temperatures. You've shrunk the leak R so much that the coherence S becomes almost permanent.
And this ties straight into the second law, right? Irreversibility. First law is the energy accounting.
Yep, the ledger.
But the second law is about the direction, the arrow of time, the unavoidable cost.
And Kelvin was crystal clear on this. The key insight, really, is that dissipation is the price of pattern. Anytime you build local structure, any synchronization S, you have to pay an energy price R to maintain it against the universe's tendency towards disorder. Understanding that R is never truly zero in the real world. That's step 1 for any practical design.
Okay, and we can see this S versus R battle in action with the Joule-Thomson effect, can't we?
Absolutely. That's Kelvin and Joule physically mapping it out. They showed exactly how gases heat up or cool down when you let them expand. It demonstrates the trade-off perfectly. Does the energy go into useful, coherent, bulk flow, high S, or does it get lost into internal jiggling, useless heat, high R?
I see.
They figured out how that S and R balance shifts depending on the gas itself, its internal workings.
Okay, so moving from the scale of heat to the scale of matter itself, those vortex atoms, that's Kelvin's big identity as motion idea.
It really is. He got inspired by Helmholtz's fluid dynamics work and had this vision. Atoms as these incredibly stable, knotted vortex loops in a perfect, frictionless fluid ether.
A frictionless fluid filling space.
Right. He thought the knot stability, which fluid dynamics suggested would conserve circulation, could explain why atoms are discrete and unchanging. Two knots are identical, they stay identical forever. Chemistry becomes a kind of applied knot theory.
It's a beautiful idea, simple, unified. But as you said, the ether didn't pan out.
Not even close. Failed every experimental test. But here's the thing. Even though the medium was wrong, the dynamics he was exploring, those survived.
How so?
Well, the mathematical tools, concepts like conserved circulation, Kelvin waves that ripple on vortices, the Kelvin-Helmholtz instability, where fluids shear past each other. These are absolutely vital today. We use them constantly in fluid dynamics, plasma physics.
Oh, wow.
And especially in things like superfluids or Bose-Einstein condensates, where you do get close to that frictionless ideal.
Yeah.
So the core philosophy that identity is a stable pattern of motion, not a solid lump that was incredibly insightful. Dead on, really.
So he had the right kind of mathematical language, just applied it to the wrong substance initially.
Exactly. And that whole line of thinking pushed him to generalize this idea of stability coming from boundary conditions. He saw how instruments, resonant cavities, even just a guitar string, they don't just vibrate any old way.
Right.
The boundaries, the physical constraints, select specific, stable, allowed ways to move. Allowed modes.
And that idea is huge, isn't it? It's the same principle selecting stable patterns, whether it's electron orbitals in an atom, giving spectral lines, or frequencies in a radio circuit, or even, I don't know, stable traffic flows in a city.
Pretty much. The boundaries dictate what patterns persist,
Yeah.
what S modes get selected and amplified, and which ones just dissipate away as R.
Okay, let's pivot to Kelvin, the hands-on engineer. He wasn't just dreaming up theories. He was out there solving massive practical problems, the transatlantic telegraph cable being the prime example. This is where RNC really hit the real world.
Oh, absolutely. That cable was an engineering nightmare. Signal loss, distortion. Kelvin was crucial. He developed the maths to model how the signal spread out and weakened dispersion and attenuation. He treated the cable as having distributed resistance, R, the leak, and capacitance,
Right.
C, the ability to store the signal's energy.
He realized the signal wasn't just a blip, but this energy pattern fighting loss and being shaped by the cable's properties.
Exactly. And it's just amazing that this telegrapher's equation he worked out in the 1850s, it's still the fundamental mathematics for how we understand signal transmission.
Seriously?
Yeah, it's transmission line theory. It governs how signals travel in nerve cells, in fiber optic cables, in the wiring on computer chips. It proves that sending any signal is always this fight between C, how well you can launch and carry the signal, and R, the unavoidable losses and noise that degrade it. The channel itself shapes the message.
But even a genius like Kelvin got things wrong sometimes. Spectacularly wrong in some cases. And those misfires, like his estimate for the Earth's age, are maybe just as important as the winds.
They absolutely are. They're incredibly instructive. He calculated the Earth could only be maybe 20 to 40 million years old. His reasoning was based purely on cooling. How long would it take a hot sphere to cool down to Earth's current temperature?
Seemed logical.
Totally logical, based on what he knew. The massive problem was he had no idea about radioactivity. This completely unknown energy source deep inside the Earth, constantly adding heat, an unaccounted for energy input.
So his energy budget didn't balance. His leak calculation, or cooling rate, seemed right, but he was missing a huge income stream.
Exactly that. The thermal model itself was fine, but the energy boundary conditions were wrong. And the lesson there is timeless. When your model doesn't add up, when the budget doesn't close, you have to rigorously hunt for missing factors, missing channels, before you just declare the model wrong or the problem unsolvable. Don't assume you know all the inputs and outputs.
And then there's this famous two clouds speech in 1900. That must have taken some serious intellectual honesty.
It really must have. Here he is, giant of 19th century physics, standing up near the end of his career and pointing out the cracks in the foundation. He highlighted two main unexplained things: the weirdness of blackbody radiation, how hot objects glow, and the failure of experiments to find any evidence of that luminiferous ether everyone assumed existed.
He called them just two small clouds on the horizon of physics.
Yeah, he thought they were minor issues that would get tidied up. But those two clouds, they turned into the thunderstorms of quantum mechanics and relativity.
Wow.
But it shows the scientific ethic in action, doesn't it? Honestly, identifying and naming the problems, the discrepancies, the leaks in your current understanding, even if you don't have the solution yet. Kelvin basically handed the next generation their homework assignment.
Which brings us neatly to his lasting legacy, maybe beyond the physics itself, this ethic of metrology. measurement as a core value.
It's about demanding rigor, that measure or hush attitude. It forces objectivity, reproducibility. Define your terms, state your uncertainties, make sure your scales are absolute and comparable. It's fundamentally an ethical stance on how to gain reliable knowledge and be accountable in design.
And his analytical toolkit thinking in terms of S, R, and C, that's just the standard language now, isn't it? From massive engineering projects right down to the quantum scale.
Completely. And it gives us concrete, testable ways to improve designs. Think about, say, building better quantum computers. The qubits, the quantum bits, they're all about maintaining coherence, S,
Right.
their main enemy. Decoherence, losing the quantum state, which is basically leak, R. So what do quantum engineers do? They create detailed dissipation budgets. They don't just say it leaks. They meticulously break down R into different channels. Is it leaking photons to the environment? Is it losses in the materials? Is it tiny energy excitations called quasiparticles messing things up?
It's the Kelvin budget approach applied to qubits.
100%. It's the same methodical spirit. Identify every leak channel, measure it, and then engineer ways to plug it, channel by channel.
That's amazing. Same method, totally different scale.
And you can stretch his telegraph maths, CNR, across biology and technology too. You can use the same type of mathematical model to analyze signal speed and loss trade-offs in a squid's giant axon or a submarine cable or a fiber optic line. The underlying physics of propagation and loss has this incredible unity. It's the method that unifies them.
So wrapping this up, the vortex atoms as a specific model died, but the thinking behind them, vortex thinking, identity as stable motion, that absolutely lived on. Kelvin gave us the scales, and he trained us in the habit. Model it, measure it, and pay close attention to the leaks.
Yeah, his successes are baked into almost every piece of reliable technology we have. But his failures, his blind spots where he couldn't account for those unknown R channels, they remind us to stay humble. But that core instinct, that what makes something itself is a persistent, stable pattern of motion. Even though the ether was wrong, that idea was right on the money. He pushed for clarity, even when it was uncomfortable.
What Kelvin was really demanding, it seems, was a kind of ethical contract for science and engineering. He basically said, look, if you can't measure it, quantify it, and then demonstrate you can beat the current design with the better one based on those measurements, well, then you're not doing physics or engineering yet. You're just writing poetry about motion.
And the challenge he leaves us with still is find the poetry and replace it with measurement.
Which raises a really interesting question for you listening right now. Where in your own world, maybe it's managing a project, developing a product, understanding a system, even just navigating daily life, where are you perhaps relying on comfortable poetry instead of digging in for the hard measurements? Something to think about.